Hi everyone, my name is Felicia. I will present CoPrompt on behalf of my co-authors, Ryan, Yuzhe, Mingming, Jian, and Zhicong. Recent advances in large language models have brought changes to the way of programming. Conventionally, programmers are used to write code line by line, but with the generation capability of LLMs, programmers can now write natural language prompts to generate code instead of manually writing it. With the generated code, programmers need to verify it to determine whether they need to modify the code, write some new prompts, or modify the prompt to generate more satisfying results. Prior work has investigated the prompt engineering process for programmers. However, it has not been discussed in the collaborative settings, where two or more programmers work collaboratively to complete a task. This contains more challenges as in collaborative programming, programmers also need to verify others' code to keep aware of their collaborators' work. They may also modify others' work to sync the process with each other and avoid conflicts with generated code. When writing new prompts, they may need to request assistance and feedback from others, and when trying to build upon others' work, there are barriers of sharing information and referring across different tasks. To tackle these challenges, we introduce CoPrompt, a prototype that supports the workflow of prompt engineering in collaborative natural language programming. CoPrompt leverages a block-based rich text editor where programmers can write natural language prompts and turn them into blocks for code generation. CoPrompt also embeds a multi-hierarchical wiki. The wiki's foldable task items provide programmers with a clear overview of task allocation and the collaboration process. Below the wiki is a message panel, where programmers can check the detailed information on others' usage mechanisms provided by CoPrompt. They can also view the history versions of a block, which includes prompts and generated code. CoPrompt assists programmers in making sense of others' complex prompts by providing semantic highlights, indicating the generation relationship between prompt utterances and code snippets. Now, let's take a look at a scenario where Alice and Bob use CoPrompt to perform collaborative natural language programming on a data analysis task. Alice is in charge of dealing with missing values, encoding, and outliers, while Bob is in charge of feature transformation and correlation analysis. Although Alice plans to finish her encoding task before Bob begins feature transformation, her progress is delayed due to technical issues. Because Alice is currently unavailable, Bob would like to start working first. With CoPrompt, Bob can create a request from the utterance encoded DF in the transformation prompt to Alice's encoding prompt, indicating the task requires Alice's encoded data frame. After filling in a simple description of the request, an icon is displayed next to the prompt and a message for this request is displayed on the side panels, when Bob can move on to other tasks. Once the system detects that Alice has completed encoding, it automatically updates Bob's prompt to leverage the encoded data to generate executable data segments. As a result, Bob no longer needs to manually modify his prompt whenever Alice updates her encoding, saving him from repetitive code updates. In case Alice needs additional time to verify the data for use, Bob decides to proactively share the data with Alice. He uses the share mechanism by highlighting his data and clicking on the share icon next to Alice's task in the wiki. As a result, Alice receives a pop-up allowing her to accept Bob's data. Once accepted, CoPrompt automatically regenerates Alice's prompts based on Bob's shared data, eliminating the need for Alice to input supplementary information herself. After encoding, Alice anticipates there may be future adjustments to the missing value handling based on her experience, which may also require updates to her encoding methods. To avoid repetitive updating, Alice creates a link connecting the data frame in the missing value handling prompt and the encoding prompt. With this link, the encoding prompt gets automatically updated whenever the prompt for missing value handling changes. When handling outliers, Alice needs to refer to Bob's correlation analysis results. To ensure no information is overlooked, Alice wants to instruct the LLM to determine the outlier handling method based on the results of the correlation analysis. To achieve so, Alice employs the refer mechanism, creating a node that links the outlier handling prompt to the correlation analysis prompt. As a result, CoPrompt updates Alice's prompts with appropriate methods, no longer requiring Alice to modify her prompts by copy-pasting and typing manually. In summary, CoPrompt introduced designs that assist programmers in comprehending collaborators' tasks and provide four mechanisms: request, share, link, and refer, designed to assist programmers in sharing information and leveraging collaborators' work to perform collaborative prompt engineering. Our user study investigated two research questions. First, how does CoPrompt support programmers to understand collaborators' work? We found that the multi-level overview assisted users to track and locate collaborators' process, generating explanations and indicating the relationship between prompts and generated content assisted participants' comprehension of prompts. And the history view allows users to have a clear overview of collaborators' changes. And second, how does CoPrompt support programmers to leverage collaborators' work? We found that request and link auto-updates reduced users' mental load. The share mechanism allows users to share knowledge both proactively and reactively, and the refer mechanism reduced the effort of carefully reading and copy-pasting. And we would like to discuss some of the aspects we found worth exploring in the future. First, compared to code, natural language expressions are easier to understand and therefore helpful for maintaining group awareness, while programmers still have difficulty in making sense of the expressions used by their collaborators when they are too vague or at a high level. CoPrompt provides a hierarchical wiki, explanation view, and the history view to assist programmers' comprehension, and it also allows users to share knowledge without losing context through the four mechanisms. Although participants find this design useful, it also increased the likelihood for the models generating excessive content, requiring participants to manually refine it. Future work could investigate better ways of interacting with LLMs to generate content without requiring extra effort. Second, CoPrompt involves a high level of automation as LLMs are in charge of comprehending. This design significantly reduced the programmer's cognitive load, while it raised concerns about the generated content, how to make generation more satisfying, and how to efficiently deal with unsatisfying results. Prior work emphasized on the importance of preserving user control when collaborating with LLMs at different granularities. To do so, CoPrompt allows programmers to manually tweak the code whenever the result is unsatisfying and provides convenient history views for each prompt for checking and rolling back. Future work could extend this design by considering more complex prompting strategies like few-shot prompts. The level of automation and controllability provided to the programmers could also be further investigated. Third, CoPrompt can be used in both synchronous and asynchronous collaboration settings. However, there are some specific challenges for asynchronous collaborations that the current CoPrompt could not fully tackle, such as preserving essential elements when automatically updating offline collaborators' work. Future work could investigate ways of balancing user control and the level of automation. Thank you for listening, and please refer to our paper for more details.